and it'll be on the title that you see.
Thank you. Thank you for organizing this this online Northeast Priority seminar. So yeah, I want to present a joint work with Pascal Maillard, which is a professor at Toulouse University. And it's about fluctuations in the front of branching Brownian motion. So first, the definition of branching Brownian motion. It's a particle system on the real line, where you start with one particle at 0 at time 0, and then it moves according to a Brownian motion during an exponential time. And then it dies, but when it dies, it gives birth to children, a random number of children that starts at the position where the parent died, and then they move independently until they die, and then they reproduce, and so on. Okay, we assume that the mean number of children is larger than 1, so that the population will survive with positive priority and will grow exponentially fast. Okay, so this is the continuous time version of the model presented by Emma just before. So that's the continuous time branching random walk. So just a few notation. We denote by n of t the set of particles alive at time t, and by xu of t the position of particle u at time t. Okay. So briefly about the motivations for this model. So Emma already said that it's a toy model for log-correlated fields. It's appearing in a different context. It's also a toy model for spin glasses, for polymers, and there is also a link with the Fisher-Kolmogorov-Petrovsky-Piskunov equation that I will mention again later. Okay, so one question that was the main topic at the beginning of the study of branching Brownian motion was to understand the position of the maximum of branching Brownian motion at time t. And so the first order is linear, so there is a velocity v for the maximum, and at time t, the maximum is roughly at v times t. Then the next order is given by a logarithmic corrective term, which is also deterministic. And then the third order, so if you look at the maximum at time t of the branching Brownian motion, you center it by this deterministic function. This converges in law to this random variable. This random variable is a sum of two random variables that are independent. This random variable g is a Gumbel distribution, which corresponds to the late fluctuation of the maximum. So of course, the position of the maximum is fluctuating at any time. So there is no hope to get something better than a convergence in law. But there is also this random variable z infinity, which, okay, this one converges almost surely. Actually, that's not a fluctuation. That's a random variable that is an almost sure limit of what occurred during the first generations. Okay, so I'm going to say more on this random variable. So what is this z infinity? It's the limits of the derivative martingale. So the derivative martingale is this quantity. It's sum over the particles at time t. There is exponential v times the position, so that's a Gibbs weight. We see the position of a particle as its energy, and that's the Gibbs weight associated to it. This is just a scaling to make it a martingale. And then there is this term, which is actually obtained by differentiating this exponential. If without this term, this would be the partition function, the rescale partition function of the system. Actually, zt is it's called the derivative martingale because it's the derivative of the partition function with respect to the inverse temperature at criticality. And for us, the critical inverse temperature is actually the velocity v. Okay, so I said that this random variable appears in the position of the maximum. So that this was proved by Lele and Selke, that proved that ZT converges almost surely to Z infinity, and that they identified the limit for the behavior of the maximum. But actually, Z infinity plays a role on many other quantities. It's really everything which occur in the front of branching Brownian motion depends on this random variable Z infinity. Actually, you can look at how many particles there are here, close to the maximum, but not exactly at the maximum. And this is described by Z infinity times the deterministic distribution. So Z infinity large really means that there have been the beginning of the branching Brownian motion was, I don't know, either a lot of reproduction or going up a lot. And so at any time after that, the front will be especially thick in terms of numbers of particles. Okay, so that's the quantity Z infinity. And yeah, in particular, that's also everything here. Understanding this is the same as understanding what occurs under the critical Gibbs measure for the system. So what is the result? The first result is the following. We were interested in the convergence of the derivative martingale to its limit and to understand its fluctuation. So it's an almost sure limit. So you can consider ZT minus Z infinity, and the goal is to obtain a new limit. Actually, you have to remove this other term, which is also proportional to Z infinity. It's not really fluctuations, it's just a corrective term. And then you have to rescale by square root of t, and it converges in distribution. The limit, so it's not a central limit theorem. The limit is not Gaussian at all. It's a one stable limit, actually. It can be written as one stable Levy process, which is spectrally positive, evaluated at time Z infinity. So actually our result contains a proof of a functional convergence for this process to the Levy process with a change in time. And also we identify precisely the behavior of the particles responsible for this fluctuation. So there are some particles which at some point go very high in the branching Brownian motion and then generate a lot of descendants, and these descendants are responsible for the fluctuations here. Okay. And the second result, the goal is to extend these fluctuations to a more general convergence. So this is the more general convergence. What does it mean? This is a result of the type of the one I said. When you look in the front, everything is deterministic up to the factor Z infinity. So here it's saying if you pick a particle according to the weight in the critical Gibbs measure, you rescale by what you need, and you look at a function of the position of this particle, also rescaled in an appropriate way. If you do so, this quantity is proportional to Z infinity, and then everything is deterministic. This is a way of saying that the distribution of particles where the critical Gibbs measure is supported is deterministic, distributed this way, and up to the factor Z infinity. Okay. So our second result, which should appear soon, is that we have the fluctuations in this convergence. For any reasonable function f, we have the fluctuations, and these fluctuations are also one stable, but just not necessarily spectrally positive. They can have any asymmetry actually. Okay, so that's it for the two results, and now I just want to give some motivations. So okay, one further question which could be asked, and which is in this first convergence that we have seen, the convergence of the maximum, could we have fluctuations in this convergence? Of course, it's already not easy to make sense of this because it's a convergence in law, so you cannot just put this on the other side. But okay, one could make sense of this question, and okay, so that's something to investigate. But actually, there are some progress with a completely different approach, which is coming from the FKPP equation. So FKPP equation is a reaction diffusion equation, which describes how a front propagates on the real line. So it's a result by McKean that says that solutions of this equation can be written in terms of branching Brownian motion. And okay, our work here is related to a conjecture by Ebert and Van Sarlos in 2000, which was that so there is a position of the front which is propagating with this equation, and there is an asymptotic development for the position of the front. And Ebert Van Sarlos conjectured that there is a universal corrective term in the asymptotic position of the front. This has been proved recently by so the first order and then even more by Graham. Okay, and because these things are related, actually there is a recent paper by Mitnick, Rockjoff, and Rizik, which state that from these previous results, they can transfer it to get results for fluctuations of the extremal process of branching Brownian motion. So it's not exactly this question, but related to it, really understanding the fluctuation very close to the maximum. So yeah, the question is, can we have, for example, a probabilistic approach for that? Can we prove this? That's the further questions. Okay, and the last thing I wanted to say is that our result is already part of these frameworks. First, Z infinity is related also to solutions of FKPP equation. And okay, Z infinity is not universal, but we see that in the development, there is a universal corrective term. So that's how our results enter this framework. Okay, thank you for your attention.
Okay, thank you very much, Michel. So we have a few moments if there are questions for Michel before we transition. Maybe I ask one question. So I guess if you look in the vicinity of this scaling limit and you let time progress, if you want to know how does the maximum change as a function of time, this can be described because you know what the point process is near the edge, and then you can just describe that in terms of that point process evolving by branching Brownian motion. Is that right?
Okay, are you meaning how? Okay, I'm not sure to understand the question.
So you're looking at a particular time at the maximum. But you could also look at the maximum as a function of time.
Yes.
Ask how does that vary? You know, what's the
process? Yeah, so it varies at scale 1 for the 1, because really the particle which is at the maximum moves as a Brownian motion. So okay, this question is really, it's not even very clear what it means and what should be the conjecture. Okay, we have a conjecture, but it's very unsure. The difference with here is that here it's the extremal process is integrated with respect to a function, and okay, yes, everything moves at scale 1, so it's very hard to see the corrective term, which should be for the 1 over square root t. Actually, here, that's very something because you have to integrate the fluctuations, and that's not easy at all. These Gaussian fluctuations are not. These Gumbel fluctuations are not at all determined. So there are actual fluctuations of order 1 that change all the time.
Transition. I'm going to stop the recording.
So, yeah.
We should transition.